Tree sort. Tree sort is a comparison-based sorting algorithm that builds a binary search tree from the input array and then does in-order traversal on the binary search tree. This algorithm called tree sort is based on the data structure binary search tree, and because of that it will be using the properties of this data structure in order to do sorting. So in case you are not aware of binary search trees or you don't know what is a binary search tree, don't worry, you have two options. I'm going to give you the same two options that I gave in heap sort lecture because the situation is very similar. The two options are, first case, if you are a long-term algorithm student, then knowledge on binary search trees, knowledge on data structures, this is a must for you. So in that case, what you have to do is, you have to first go to our data structures lecture series. There you will see binary search tree lectures. So in those lectures, we have clearly detailed about the data structure binary search tree, and you will get complete details on what all manipulations you can do on that. And after that, if you come back here, whatever is going to be done in this lecture will be very easy for you. And one more thing, you also have to be clear about in-order traversal. So if that is also not clear, please go to the in-order traversal lecture that is also under data structures lecture series. So if this is not the case with you, if you are a student who is here in order to, let us say, write an exam tomorrow, if you have your algorithms exam tomorrow, or you just want to know about tree sort, you're not concerned about the rest, then you can just continue with this lecture. What we'll do is, whenever we need some concepts on binary search trees or whatever, we'll just touch upon those so that you understand tree sort. Okay, so this is what we're going to do. Let us start with tree sort. So in tree sort, what are we going to do is, first thing we said, we'll be building a binary search tree. So after building binary search tree, you want to do in-order traversal. The first question is, how are you going to sort by doing this? The reason is, binary search tree, it has a property. First of all, what is a binary search tree? In a binary search tree, you'll see the special property in this tree that whenever you are at any particular node, the node on the left of it will have a value lesser than parent, and the node on the right of it will have a value larger than parent. So this will be followed throughout the tree. So you go to any particular node in the tree, if you have a left child, that will be having a value lesser than this particular node, and if you have a right child, that will be having a value larger than this particular node. And this is true for the complete subtree as well. If you have this particular node, if you go to the left subtree, you will only find values which are smaller than the value of this node. So this is what a binary search tree is. And there is a property of binary search tree which says, if you do in-order traversal on this binary search tree, you'll always get a sorted list. So what is in-order traversal? In in-order traversal of a tree, you'll first go through the left subtree of the tree, then you will go to the root of the tree, and then you will come to right subtree. So this particular order, if you recursively follow, you will get in-order traversal. Let us understand this by taking an array. If this is your array, what are you going to do first? The first thing is, you will go to each of the values in this array and you will build a binary search tree. So let us say you build a binary search tree which looks something like this. If this is your binary search tree, next step is to do in-order traversal. The point you complete in-order traversal, you'll get a sorted list. What we'll do is, we'll take numbers and we'll see a dry run of this tree sort algorithm. Then the whole process will be clear for you, how each number is getting manipulated. So consider this as your initial input array: 42, 70, 12, 30 and 24. This is your initial input array. What is the first step? From this input array, you have to create a binary search tree. So first I'll be looking into 42. 42 will be the root of my tree. Next, I'm looking into 70. How will I add 70? 70 is larger than 42. So I should go to the right side of 42. So I'll add 70 here. So this is how you'll insert into BST, a binary search tree. Whenever you want to insert, you'll go to the root then you will keep looking for whether the number is smaller or larger. If it is smaller, you will go to the left side. If it is larger, you will go to the right side. So you will recursively continue doing this. Whenever you see an empty position, you will insert it there. What about 12? How can you insert 12? If you look at 42, 12 is smaller than 42. What will you do? You will go to the left side, insert it there. Next number is 30. So how will you insert 30? 30 is smaller than 42. So you will go to the left side. 30 is larger than 12. So you will go to the right side of 12. 30 will be inserted here. What is the next one? Next is 24. 24 is smaller than 42. So you'll go to the left side of 42. 24 is larger than 12. So you will go to the right side of 12. 24 is smaller than 30. So you will go to left side of 30. So 24 will be kept here. So this is your binary search tree that you built from this particular input array. Once you have the binary search tree, you no more need the input array. What do you have to do? You have to do in-order traversal. So in in-order traversal, you have to first go to the left subtree. After you complete the left subtree, you will go to the root. Then you will go to right subtree. And this process you have to recursively follow. So for this, I had given you a trick in our in-order traversal lecture. So here we are going to use that trick because otherwise we'll be wasting good amount of time in doing this complete procedure. So using that trick, we'll directly find out what is the final order. Okay. So the trick was this, that you will start going through the tree from here. Whenever you visit a node for the second time, at that point, you'll note it down. This is the trick. So you are starting from here. You visited 42 for first time, 12 for first time, 12 for second time. Second time means you have to note it down. Again, you are coming here, visited 30 for first time, 24 for first time, 24 for second time. So you noted 24 down. So this is the in-order traversal we are doing. Again, you visited 24 for third time, 30 for second time. So write down 30. You are again going on 30 for third time, 12 for third time, 42 for second time. So whenever you visit second time, note it down. Again, you are going here 70 for first time, 70 for second time. So note down 70. Continue your traversal, 70 for third time, 42 for third time, and you are done. So at this point, whatever list you got, this is a sorted list. So this is the in-order traversal of this binary tree. And the list that you got is a sorted list. So this is how you sort using tree sort. Next thing is we have to write the algorithm and then we'll see time and space complexities of this algorithm. So let us go into time and space complexities. So first we have to write the algorithm. What is the algorithm? You have to simply create a binary search tree, insert all elements into the binary search tree, do an in-order traversal. Simple. So this is the tree sort algorithm. In tree sort of array. So on this given input array, you are going to do tree sort. What is the first step? Initially, you just have to create an empty BST. So create empty BST, binary search tree. So I'm just writing this. Practically, you will keep inserting elements one by one. So for each element, what do you have to do now? For each element in array, for each, let us say, element in the given input array, what should you do? You should insert it into binary search tree. So for that, we'll write a function, let us say BST insert or something. We'll write this in detail. BST insert. What will this BST insert function do? It will insert one particular node into the one particular value into this tree, binary search tree. So you have this BST insert function. In this, you will have to give the root of BST. So whatever you created, here when you create, you will get root. So that root you are going to use root, and then let us say you have to insert element. So element. So you know you have to insert the value called element. So element is one element of your array. you're picking one element each and inserting it into binary search tree. Once you insert it, what is the next thing? You have to do in order traversal. So in order traversal of the binary search tree of root. So whatever is the root, that is the identity of your tree. That is why I am writing root in all these places. From the root, you will start the traversal. You will traverse through the complete tree, get the complete in order traversal list. So this is the complete tree sort algorithm. Only this much is the step. Now we will write these algorithms separately: binary search tree insert and in order traversal. So first step is create empty BST. Then you have to go to each element of array, and for each element you have to insert it into the binary search tree. And once you insert it, what will you do? You will do in order traversal of the binary search tree. So let us see the BST insert algorithm. What will you do in the BST insert algorithm? BST insert. In BST insert, what do you have as inputs? You have root and you have some value. So that element, let us call it as k now. So k is the value that you have to insert it into this binary search tree. So what are you going to do? So the first step is if this root is null, then what will you do? If this is the first element, you simply have to create a new node and put value k into it. So BST insert, I'm directly going into it because we already discussed BST insert in BST lectures. Here we'll just detail the process. So you'll understand even if you have not gone to that lecture. But if you want complete explanation, please go into the BST insert lecture. So what we are going to do first, if it is null, if not root, that is if root is null, what will you do in that case? In that case, you want to create node, and that node should have value, let us say k. So this particular k, you will point to root and return. So this is what you will do in case root is not present. If root is not present, if root is present, what will you do? You will check whether the value pointed by it is lesser than or larger than this value k. So if your value k is lesser than root pointing data. So whatever be the value in the root, if k is lesser, what do you have to do? You have to go to the left side. So whenever you are going to the left side of a node, you have to check whether left side is present or not. If there is no node present, you have to create a new node and enter your value. If there is a node already present, you have to first go to that node and then recursively do the same process. So first thing is you have to check whether there is a left child present. So if root pointing left, if left child is present, then what should you do? You should recursively do BST insert on the left child. So if it is present, then you should do BST insert on the left child, root pointing left. On root pointing left, and what is the value to be inserted? K. So here you are calling the same function. This is recursion. What is the next thing to be done? If left is not present, that is in else case, what will you do? You have to create a new node and put it in root pointing left. So in root pointing left, you will do the same thing. You will create a new node with value k and put it there. Okay. So I'm just writing create node with value k. Okay. You have to create a new node and put it in root pointing left. What is the next thing? You have to look for root pointing right. So if this condition is not met, that is if this condition is not met, that means k is larger than node pointing data. So if your value k is larger than root pointing data, in that case, what should you do? If the value of k is larger, then you have to go to the right side and you have to do the same procedure. If right side, if there is a node present, you have to recursively do BST insert. If there is no node present, you have to create a new node and add it there. So if there is a node present, if root pointing right is present. If root pointing right, what should you do? If root pointing right, you should do BST insert recursively. BST insert on root pointing right. Root pointing right. And what is the value to be inserted? It is k. And what about the else case? If right child is not present, you can make your node as the right child. So in else case, root pointing right is your new node that you will create with value k. So create node with value k. So this is in case right child is not already present. Okay. So at this point, once you have checked for left child, if it is lesser than, greater than, both cases you have checked. See, if you have an equal to case, that you have to add in either of this. Maybe you can put an equal to also here. Initially, we were considering that there is no same element won't be repeating again and again. If it is the, you have to put that less than here or here. In both you can put, that is implementation dependent. The next thing is, if this is done, then you can return. So what will you return? You will return the root node, because always in a tree, root is the identity. So after all your work, you have to return root. So what happens in this algorithm? In BST insert algorithm, you are simply looking, first of all, you will look whether root is null. If it is null, you will create a node there only. If only one element is there, that is it. Otherwise, if there is a, if it is not null, that means some root is there. What will you do? You will stand on the root and then you will check whether the value k that you are having, the element you want to insert, that value, is it lesser than root? If it is lesser than root, you have to go to the left child. Check whether left child is there. If it is there, recursively do binary search tree insert on left child. If it is not present, create a node as the left child with the present value. If k is greater than your root, that is whatever data is there in root, go to the right side of root. If right child is present, do BST insert recursively on the right child. If right child is not present, you have to add new node on the right side. So this is the algorithm in order to do BST insert. So what is missing now? Only part missing is in-order traversal. So let us do in-order traversal algorithm as well. How do you do in-order traversal? In order. So I know you already know in-order traversal, but I'm doing this for completion. In order of, what do you have? You have root. So I'll call node root, whatever you can put. So root. How will you do in order traversal? If root, if it is not null, what will you do? You have to first go to the left child. So you will recursively call in order of node pointing left or root pointing left. So you are going to the left child first. In order, what did we say? Go to the left subtree, then the root, then the right subtree. This is the rule for in order traversal. So first you went to the left child. How will you go to the left subtree? You will recursively call it on the left child. So that will go to the left subtree. After that, you can go to the root. Going to the root means printing the value. That is the purpose here. So you will print value at node. Print, let us say, root pointing value or root pointing data, whatever it is. Whatever is the data in root, you have to print it. And after this, you have to call in order on root pointing right. So when you do this, your in order traversal is completed. So in order traversal, what are you doing? If the root is present, you will go to root pointing left in recursively. Then you will print the value. Then you will go to root pointing right. So you may have a doubt on whether we have to check whether root pointing left is existing or not. So in our algorithm, we are having this null check initially. So we are entering the process only after null check. So what happens? Even if root pointing left is not present, when you call it recursively, it will go to that call. In that call, it will exit here. So that is what is going to happen. So this is the in order algorithm. Let us see the whole algorithm once. So in tree sort, let us see what all we have done. So first of all, create empty BST. Then for each element, you have to insert into BST. After that, simply do in order traversal. Insert into BST. We already saw how do you insert. You have a value k to be inserted. So if there is nothing at all, it is an empty tree, insert at the root. If it is not, what do you have to do? Check whether the value is lesser than whatever is there in the root. If it is lesser, you have to go to the left side. If left child is present, recursively do insert on left child. Otherwise, create a node and put on the left side. Do the same on the right child. And after that, that is in case k is larger, then do the same on right child instead of left child. Then you have to do once your complete binary search tree is insertion is done. That is, calling this once will insert only one element. So here you are in the loop, you are calling again and again for each of the elements in the array. So when you complete it, all the elements of the array will be inserted into binary search tree. After that, you can do in order traversal. So in order traversal, what do you have to do? In order traversal, first go to the left subtree, then print root, then go to right subtree. It's as simple as that. So next thing is, we want to understand time and space complexities of our algorithm. How do you find time and space complexities here? So we already know BST insert, it takes order of n. So for each of the BST insert, order of n in worst case is the scenario. So what we are going to understand here is, one is worst case and one is average case. The reason is, average case is of importance for us because in a BST, if it is a balanced BST, if this BST is balanced, or binary search tree, if it is balanced like this, then the height of this tree will only be log n. If it is not balanced, if it becomes a skewed tree, this is also a tree. If all the nodes are on one side, then the height of tree is order of n. So this will make a huge difference in the time complexities, whether it is a balanced tree or if it is not a balanced tree. So in average case, you can always consider balanced tree because mostly BSTs will be balanced, like somewhat balanced. But still, when you look for worst case, you have to consider unbalanced tree. That is where order of n comes in for each of the BST insert. So my point is, if you are having a balanced tree, in that case, each of these BST insert, first let us see unbalanced. Normal unbalanced case, each of the BST insert will take order of n time. And how many times are you calling it? Order of n times. So totally order of n into order of n, your time complexity is order of n square. So this is actually the worst case time complexity of tree sort. And this in order traversal, it is going to take order of n. So we are not counting it because we already have an n square term here. So again, no point in adding order of n. So order of n square is actually the worst case, but we have an average case of order of n log n. So how are we getting order of n log n? Because if this BST insert, if this thing is in a balanced binary search tree, if it is balanced, then we can count it as order of log n. So then you will be doing order of log n into order of n. It will be order of n log n. So this is the average case. What happens is mostly average case will be hit. So that is the importance of this algorithm. In average case as well as best case, you have time complexity order of n log n. Worst case is order of n square. And if you are using balanced binary search tree, then you can take even worst case to order of n log n. So that is it about time complexity. What about the space complexity? Space complexity also you should be aware of. So what is the space complexity of this algorithm? One space taking process is creating BST, because you are having an input array, you are separately creating a complete BST. So you want space for all the n elements to be part of the BST, which means you will take extra order of n space for construction of BST. Is that all? One more thing is recursion. Your BST insert is recursive procedure, and recursion will take space order of height of the tree. So height of the tree, in worst case it is order of n, in average case it will be order of log n. So space complexity is order of n only because worst case is that. order of n anyway you are using here for BST. So even if recursion stack also takes order of n, still the total space complexity is order of n only. So your time complexity is worst case order of n square, average case order of n log n. Space complexity is worst case order of n.